Okay, now let's see what this would look like in the case where A is a 4 by 4 matrix. What would a minor or a cofactor look like in this case? Well, let's start by writing down the minor of this matrix A corresponding to the third row and the second column. So remember what that means? The minor, the ijth minor, so in this case it's 3, 2 minor, that's going to be the determinant of what you are left with if you delete the third row and the second column of the matrix A. So you can see you'd be left with a 3 by 3 matrix. So this minor is going to be its determinant. So it's going to be the determinant of 1, -2, 0, 4, 3, 3, and then 0, 2, -1, right? Because you can see those would be the entries that I had left over if I were to delete the third row and the second column of this matrix A. So that's going to be the 3, 2 minor of this matrix. Now what about the cofactor? Well, the cofactor in the third row, or the cofactor corresponding to the entry in the third row and the second column, that's another way to read this out loud. Well, remember the formula? It's -1 to the power of 3 plus 2 times the minor in the 3, 2 position, right? All I'm using is this formula right here. Cij is equal to -1 to the I plus j times mij. So this is the formula that gives meaning to the cofactor, and that's what we're using. So that's what's down here. So what can I do? Well, -1 to the 3 plus 2, this is really -1 to the power of 5. So -1 to the power of 5 is an odd power of -1, so the result is just going to be -1. So what you get here, that's just going to be a negative sign, and then the M32 is just what we worked out over here, so we get negative times the determinant of 1, -2, 0, 4, 3, 3, and 0, 2, -1. And that is as far as we can go at this stage, right? Notice I stopped here with the minor. I didn't go further to actually compute this. And the reason is we just don't have a method for doing that yet. I haven't yet given you a satisfactory definition for the determinant of a 3 by 3 matrix, right? We can only do determinants of 2 by 2 matrices so far. So at this stage, the best we can do is write it down symbolically. But that's what you would have. This is symbolically what the 3, 2 minor would be, and then this is what the 3, 2 cofactor would be over here. Okay, let's do one more example. Let's do the 4, 4 minor and the 4, 4 cofactor. So the 4, 4 minor of this matrix, well, this time I would want to see what I am left with if I were to delete the fourth row and the fourth column. Just copy those index. So the fourth row and the fourth column. The first number always corresponds to the row, and the second number corresponds to the column. Okay, so in this case, you'd have the determinant of what's left over. You'd have 1, -1, -2, 4, 2, 3, and 3, 5, 1. And again, that's as far as you could go, right? Because we can't actually evaluate this any further, but we can at least write it down. And then the 4, 4 cofactor would just be -1 to the 4 plus 4. Just add your indices as an exponent times the 4, 4 minor. Okay, and then just do what you can. At this stage, -1 to the 4 plus 4, that's -1 to the power of 8, which is an even power of -1, so hence it evaluates to +1. And then the minor over here, the 4, 4 minor, is what we have over here. So it's really just going to end up being the determinant of 1, -1, -2, 4, 2, 3, and 3, 5, 1. And again, we can't go any further than that, right? That's the best we can do at this stage. Until we have a concrete method for actually evaluating 3 by 3 determinants, we can't go any further than that. But soon we will. Soon we'll be able to. Next, what we're going to do, remember what our goal is here. We want to use a definition, a theoretical definition of determinants of n-1 by n-1 matrices to come up with a definition for determinants of n by n matrices. And we're going to use cofactors to accomplish exactly that. Okay, so how are we going to do it? We're going to define something called cofactor expansion. So start with this definition. We're going to start with the matrix A. It's an n by n matrix, and we're going to let I be some index of, or be the index of some row, and let j be the index of some column. So I would have to be a number between 1 and n, and j has to be a number between 1 and n as well. Okay, so what I'm going to define first, I'm going to write down a formula for the cofactor expansion of this general matrix A along the ith row. And the definition is as follows. We're going to use sigma notation for this. So we're going to do a sum, and we might as well use the letter k for the index because I and j are already reserved for something else. So we're going to take the sum from k equals 1 all the way up to n, and here's what we're going to take the sum of. We're going to take the entry from the matrix A that's in the ith row and the kth column. Okay, and we're going to multiply that by the ik cofactor of the matrix A. Okay, so remember, what are these indices I and k? Well, I is the index that points to the row that we're expanding along, and k is the index of summation here. So I is the only index that's actually fixed external to this expression, because really, if I were to, I could expand this sum, which I actually think helps a lot. So let's expand this sum. Remember how you do this? You take this expression, and you take your starting variable down here, and you plug in k equals 1. So I plug in k equals 1, I'm going to get a I1 C I1. Okay, then the next thing I'm going to do is I'm going to increment the index k so that it's k equals 2, and then I'm going to plug in k equals 2 to this expression, and I'm going to get the entry from the matrix A in the ith row and the second column multiplied by the cofactor corresponding to the ith row and the second column as well. I almost messed that up there. So that's supposed to be the entry from A in the ith row and the second column multiplied by the cofactor corresponding to the ith row and the second column. And then I keep on doing this, right? You can see here we had 1 as the second index for both of these. Here we have 2 as the second index. The next one we'd have 3 as the index, and we'd have 3 for the second index and I for the first index. And you keep on going until you get to the very last one, which, remember what the last term is? It's the one you stop up here at whatever the stopping point is here, which was n, the number of rows and columns of A. So our last one is going to be the entry for the matrix A in the ith row and the nth column multiplied by the cofactor of A corresponding to the ith row and the nth column. And that's your formula for cofactor expansion of A along the ith row. Now this is intimidating the first time you see it. And it is a little bit hard to wrap your head around what exactly is going on. But so is matrix multiplication, right? When we define matrix multiplication, when I first showed you the formula in terms of summation, it's a little bit hard. It was hard to wrap your head around that too. But once you see it, once you actually see it happening, it's a little bit more straightforward. So have faith that this will make sense once we see an example, if it doesn't make perfect sense just yet. What I would like you to make sure you're convinced of right now, though, is just make sure you're convinced that this does actually compute to something, right? The only thing that these symbols are dependent on is the matrix A and the row that you choose to expand along. So if I choose to perform cofactor expansion of A along the first row, well then all of these i's would be 1, right? And all of these symbols would then either reference particular entries of the matrix A or a particular cofactor of the matrix A. And that's all I want you to be convinced of right now. Okay, and that's cofactor expansion along a particular row. But we can also talk about cofactor expansion along a particular column. And it's actually going to be similar. Here's what you get. It's the sum. We're going to do another summation. The sum from k equals 1 to n. But here, this time, we're going to let this index range through the rows instead of the columns. So what the expression we're going to add up is the entry from A in the kth row and the jth column multiplied by the cofactor of A corresponding to the kth row and the jth column. So it's the same idea, but we just this time the column is fixed and we let k run through all the rows and we add up each term that we get corresponding to each index value of k. So what's the first value of k? K equals 1. If I plug in k equals 1, I'm going to get the entry from A in the first row and the jth column multiplied by the cofactor of A corresponding to the first row in the jth column. Remember, J is a fixed number external to this expression. It is the index of the column for which we are talking about cofactor expansion along. So it's some fixed number that would have been decided in the background between 1 and n. Okay, and what's the next value? We'd increment k to k equals 2, and we'd get the entry from A in the second row and the jth column, multiplied by the cofactor of A corresponding to the second row and the jth column, and so on, right? We would keep on doing this until we got to our final value of k, which would be equal to n. So I would have the entry from A in the nth row and the jth column multiplied by the cofactor of A corresponding to the nth row and the jth column. Okay, finally we got that sorted out. Okay, so really there's actually a different, at least theoretically, there's a different definition here for the cofactor expansion of A along the ith row. There's a different definition for every single row, right? There's no reason to expect that if you change rows, you're not going to actually change the value of this expression, right? If I choose one value of I between 1 and n, I might get one value for this expression, but what if I choose I to be another value between 1 and n? Or another value, right? I might at least in principle, there's no reason to expect that I wouldn't get a different value for each choice of row. And same with the columns. There's n different columns. If I'm talking about an n by n matrix, I can go with column 1, column 2, column 3, all the way up to column n. There's n choices for this value of j. So it's conceivable that each of those values of j would make this expression come out with a different result. But that's why this theorem down here is so surprising. And it says the following: let A be an n by n matrix. The cofactor, and here's the claim, the cofactor expansion of A along any row or column is going to yield the same result. That means if you use either of these formulas, like if you use this formula up here, you have to choose a value of I between 1 and n. So you have n choices for the first formula. If you compute this formula, if you compute the cofactor expansion of A along a column, you have n choices for columns. You can choose j to be any value between 1 and n. This theorem is saying that no matter which formula you choose, no matter which value of I you choose in the first formula, or no matter which value of j you choose in the second formula, you're going to get the same result no matter what, which is really not obvious if you think about how much is here, right? And once we get to some examples on the next page, I promise you it still won't be obvious why this theorem is true, or why these are going to be guaranteed to give us the same result no matter what we choose for our index I in the first case or j in the second case. So it is actually a really surprising result that these two expressions are always equal, and that is actually why we're able to use it to complete this following definition, where I can finally actually give you once and for all a good definition for a determinant. So the determinant of an n by n matrix, A, which we denote by the same thing as before, just DET, short for determinant, and then put A in brackets afterwards. And it's given by just simply take its cofactor expansion along any row or column. And it won't matter which one you choose by the previous theorem. Right, so let's think about this. Remember what we said we were going to do? We said we were going to give a definition for determinants of n by n matrices, and what it was going to depend on is that the definition of n minus 1 by n minus 1 determinants were already defined. And that is where the cofactors come in. Because remember, the cofactors, each of those cofactors are going to be determinants of n minus 1 by n minus 1 matrices, and that's how that ties together. Okay, so we really have completed our goal. We've completed the second step. Where is it? Here it is. We've actually completed this second step. We've assumed that determinants of n minus 1 by n minus 1 matrices are already defined, and then we use those to define the determinants of n by n matrices. Okay, and where that shows up again is the cofactors, because the cofactors really have determinants of n minus 1 by n minus 1 matrices built into them. Okay, let's look at an example in the next clip.